I'm going to talk about computational fluid dynamics. What is that? And that early in the morning. What I'm going to do is I'm going to show you a difference between IR heating and heating with unit heaters. We'll take the same space and we'll put the Roberts-Gordon IR heaters there, and we'll put unit heaters. And then we will put the microscope on that space, and we will see how the temperature looks like in that space. Not just at one point, not just at one location, but all locations in a 3-dimension that you can never measure with your thermocouples. Nobody can do that. What I'm also going to show you, how the air flows in that space when you have unit heaters and when you have IR heaters, and what difference it makes in the comfort of occupants. Finally, why do we put the heaters? We want to make people comfortable, correct? Yeah, and then how do we do that? And I'm going to show that to you. In addition, I'm going to show it to you what's the difference between the current design of that reflector and the new design of the reflector, okay? So let's start with the basic here. Heat moves from the hot location to the cold location. There are 3 modes of heat transfer. Conduction. When the pan is on the stove, don't touch it. Why? It's conducting the heat. It's by molecular handshake. It means one molecule of that solid gives heat to the next and so forth. The next one is the convection. When that kettle is sitting on the stove, yeah, the kettle is getting heated by the conduction, but the water or your tea or coffee in that kettle is getting heated by convection current. So these molecules dance on the surface of that kettle, and then they transfer the heat from the kettle surface to the liquid surface. Well, unit heaters, they work mostly on this principle, that is the convective heat transfer. The next one is the radiation. These 2 modes, conduction and convection, either they need solid or they need some fluid to transfer the heat. Radiation is very different. You can transfer the heat even in vacuum. What they do, they transfer the heat from the hot surfaces to the cold surfaces just by sending the photons, what they call it, the wavelengths, from the hot surface to the cold surface. So really, it doesn't need medium. It happens without medium, and it happens between surfaces, from hot surfaces to the cold surface. And IR heaters, they work on this principle. Though there is some convection component that you can't avoid, but it's mostly based on radiant heating. Do you remember our first flight when human beings went into the air? People thought there is some magic fuel they are burning that's lifting you up. That's not the case. That hot air goes up. Hot air goes up. Why? Hot air is lighter than the cold air, and it rises up. It's called thermosiphon. It's the buoyancy effect that pushes the hot air up, and as the hot air goes up, it brings the cold air in. And that cold air becomes hot, and then it goes up. So this is the thermal siphon. Remember, once the hot air goes up, it sticks to the ceiling like a helium balloon, okay? Like that Spider-Man there. Well, you need some pull to bring that hot air down. I don't know whether you can bring the Spider-Man down, but that's a different story. Well, let's look at computational fluid dynamics. It is a science. It's not magic. It is not statistical analysis that people collect the data. This is based on sound principle of engineering, heat transfer that we all know. The equation of motion, equation of heat transfer, conservation of mass, conservation of momentum, conservation of energy. We all know that. I wish we could solve that on our calculator or on your iPad. We cannot do that. Still, we cannot do that. Mathematics cannot solve those equations. So we use the computational method to solve this equation so it can simulate fluid flow, not just the air. It can simulate flow of water. It can simulate blood flow if you are designing a heart valve or heart pump. It can simulate slurries, what happened in the Japan earthquake and the tsunami. It can simulate heat transfer, mass transfer, even chemical reactions. We can put the fire in a virtual building and predict where the smoke is going. What do we get out of this CFD analysis? Can you see how the air is moving in this space? Can somebody tell me? We cannot. And the day you will get that vision to see the air movement, you will put me out of business. Okay? So computational fluid dynamics helps you to visualize airflow patterns. It helps you to visualize where are the hot spots and cold spots in the space. It helps you to understand how people will feel in that space, whether they are too hot or too cold. You can predict the RH. You can predict the contaminants like CO2, CO in some cases in parking garages, and finally the smoke movement in the space. So let's get to the business. Let's compare IR heaters versus unit heaters. This is the CFD model, simple room, 50 feet by 100 feet, and there are two doors, and these doors are closed, and we put the Roberts-Gordon's IR heaters there. You can see that. Now the idea is to simulate this and see what's the heat distribution, temperature distribution, airflow distribution in the space, and the heat input is about 200 K BTUH. Let's take the unit heaters here. You may be familiar with that. 2 unit heaters placed in the corner of the room. And then the output is same. Remember, 200 K we are putting through the unit heaters. I call this as the steady state model. There are different ways of simulating this. What is steady state? That these heaters are working for a long time. Doors are not constantly opening and closing. The wind is not blowing and changing its speed and direction. And the design temperature remains same outside. So this is kind of a snapshot, if you will, in a time. This is the new reflector we put it in. This is the unit heater. You can see there is a supply on front, written on the back. So it blows the hot air, then they sucks the cold air back. And they try to direct the hot air direction kind of down towards the floor where the people are. Let's look at the thermal performance first. What you see here is a color picture of temperature distribution at that location. Hereafter, I'm not going to tell you red is hot, and should I say, not just hot, but infrared hot, correct? I got that. I got that. I got that. Okay. So red is hot and cold is cold. The blue is cold, okay? So what you are seeing here, importantly, you can see that green color, which is between 70 to 75, 72 degrees Fahrenheit. And then note near the floor, you don't see any blue color there, okay? Now when we go to unit heater, look at that, the cloud of hot air just sitting up near the ceiling. Hot air goes up, hot air goes up. And then you can see that blue strip near the floor, because unit heater works on the principle of convection, not radiation. When you use Roberts-Gordon's infrared, they heat the floor first, and then that heats the air. Here we are trying to heat the air with the hot air, okay? So you see that floor is very cold. You can look at it from different angles at different locations. Look at how uniform that green color is. That's what you want. There is no blue spot on the floor. When you go to the unit heater, that red color is right from the ceiling to about 10 feet down. This is a 20 feet high room. And look, that blue spot, the blue strip is consistently there everywhere in the room. If we go 4 feet above the finished floor, you can see green color there. So average temperature is about 74 there. If you go to unit heater, it's blue. That's why people complain it's cold. It's cold, cold feet. Now, that is 72 degrees. The other way of looking at this data, the simulation data, is that to see all the places where the temperature is 80 Fahrenheit. We can do that with the CFD because you don't need thermocouples in a virtual space. I have all the data, and I touch all the data and find out where is my 80 Fahrenheit location. And what you're seeing here is those are the two big clouds hanging over there near the ceiling. But importantly, look near the floor. Also, you have 80 Fahrenheit cloud there. On the side walls, you have few clouds of 80 Fahrenheit. When you go to unit heaters, there is no red cloud on the floor, neither on the walls. All that red cloud is hanging up near the ceiling because hot air goes up. Hot air goes up. Have you heard the word thermal stratification? Thermal stratification means cold air sits near the floor, hot air sits near the ceiling. And higher the stratification, more air will be sitting near the ceiling and colder air will be sitting near the floor. Remember, we have same amount of heat of 200,000 BTUs going both in IR heater space and unit heater space. Keep that in mind. With that, you can see that unit heater, the red line, the temperature on the floor is somewhere around 40 degrees, 45 degrees. It picks up slowly, keeps on going up, and once you reach 10 feet height, 10 feet elevation, it just remains there at 85 degrees, 86 degrees. And then as it sees the cold ceiling, it again drops back to 45 degrees. With Roberts-Gordon IR heater, what you are seeing here is you are not starting with 45 degrees. You are starting at 68. So your floor is not at 45. The same space, same heat loss from the envelope, same heat input. But with IR heater, since it is heating surfaces first and then the air, you can see our floor is much warmer, much hotter than the 45 degrees one. Then it's going up and almost straight. It's not heating up as it goes. And you saw that in color pictures. So it's about 72 degrees, and then slightly it goes up, and again it sees the cold ceiling there. So you can see when people say IR heaters they give relatively low thermal stratification, you have the proof here. Let's look at the wall temperature because that's what is important in case of IR heaters. This is with the IR heater, average is 71. With unit heater, average is 46. Remember, blue color is cold, okay? The roof temperature with IR heater 63, 52 with the unit heaters, sidewall temperatures 58 average on the sidewalls. It's about 48 with the unit heaters, and then other walls you can see 63. See how that new reflector is working? You see that image on the sidewalls where those two lines are coming from? It's the impact of that new reflector design that's hitting the sidewalls. Here is the unit heater, again blue. Let's look at the airflow patterns, how air is moving in these two spaces. At 4 feet from the finished floor, when you look at it, what you see, these are the 4 beautiful looking airflow patterns, 4 loops. What's happening is hot air goes up, pulls the cold air with it, and then as it goes up, it gets cold, and then it moves sideways. It creates that churning effect And you know what churning means? It means good mixing. You need good mixing that gives you uniform temperature in the space. Let's look at it. See, these are the hot spots on the floor. That air is going up, and it's pulling those blue lines with it. It's pulling the blue lines with it. As it pulls the blue lines, it goes up, and then it stays there, and it moves sideward and creates that churning effect, the mixing effect in the room at 4 feet level. And that helps in bringing the temperature uniform. Well, with the unit heaters, of course the air moves, but it creates the huge tornado there. You see that? The eye of the tornado is right in the center of the room. What it does here is, you can see, and please don't take my word, that hot air goes up. That hot air is going up. So as the hot air comes out from the heater, no matter what angle you put it down, it's first going to go up. And that's what you see here. The hot air goes up, hits the ceiling, and there is a throw. You remember they call the throw from the heater? The throw is so high from the heater that jets hits the opposite walls, and those walls are cold. So the hot air, when it hits the cold wall, it gets cold. And then as it moves along the walls, and then it comes down. So what you're getting at the lower level is the cold air from the heater, from the unit heater. Well, as I said, finally, these are all good color pictures, good animation. Tell me, how am I going to feel in this space? That's what is important. That's what your client sees, correct? Well, what is thermal comfort after all? It is a state of mind. So as the thermal comfort. It cannot be measured, but it's a subjective thing. But scientists in the world, they try to correlate thermal comfort with different parameters. Your activity level, where you are sitting in your office, whether you are in the gym or where you are in the factory, the clothing level, what you are wearing, air temperature around you, the wall temperature around you, the radiant effect on you, humidity level. If it's too humid, you feel uncomfortable. And of course, the airspeed. You know, people put the ceiling fans. The ceiling fan is not a cooler. It's just the air movement, the sense you get of cool with the higher airspeeds. Well, ASHRAE standard 55. How many of you know that? Okay, few of you. But now you will know. This is the standard for thermal comfort of occupants. And that standard gave us two indices. One is called percent mean vote. So if you survey the people, they tell you whether they feel hot or cold, and then you measure the surroundings, their clothing level, and correlate it. This is statistical thing. Well, the index of PMV, what we call it, goes from -3 to 3. -3 is a blue color. People will complain it's very, very cold. When it's 3, people will complain it's very, very hot. So ideally, we want to be at that 0 number, what we call thermal neutral environment. People are happy in that environment. So we want the green color. And we are at 4 feet height above the finished floor with the Roberts Gordon IR heaters, putting 200,000 BTUH in that space. Look, more or less, it's a green color. On an average, it's kind of -0.2, close to 0, correct? People will not complain they're too hot or too cold. Let's go to unit heater. What happens? The average is -2.5. Remember, -3 is too cold. What is -2.5? It's cold too. So why is that? Same, I use the same clothing level. I use the same 200,000 BTUH in the space. It is because of that tornado. Remember that tornado, I showed it to you? high airspeed around you, and then the air temperature was very cold. Wall temperatures were very cold. The radiant effect was almost none there. In fact, it's an adverse. The cold wall is radiating on the occupant. That's the reason this is blue, very cold. Well, this is going to get even better now with that new reflector design Mark was talking about. So I did the simulation side by side with the current reflector and the new reflector. So let's look at this is the current design of the reflector, space temperature, and mark those colors. Look at this, the difference here. Look at what happens inside that reflector. You see that red hot tube is there, and this is the airflow in that reflector, how the air moves. We can even animate that, and you can see what that tube is doing is it's pulling the cold air around it, and it's going around it and going around the reflector and going out. This is the current design, the wall temperatures, the floor temperature, and this is the new design, the current design and new reflector. On the side walls, current one and the new one. You see the color difference there. Current and new. On these side walls, current and new, current and new. And then this is the current design. Now, we can also predict how much radiation energy is falling on different surfaces. So if I compare how much incident radiation is coming on that floor, this is the current, this is new. Current, new. On the walls, current, new. On the side walls, current and new, current and new. And then, finally, this is what I thought. If you put 200,000 BTUH in the exactly same space with the same heat losses from the wall, this is what you will get. This is with IR heater. More than 90% people will be happy. And here, only 8% people will be happy. Okay? So this side-by-side comparison with the unit heater. So as Mark said, my company's name is AnSight. It means insights through analysis. And I want to transfer some of those AnSights to you. So in summary, IR heaters work on the principle of radiation heat transfer. It is surface-to-surface radiation. Unit heaters employ air movement, hot air movement, to heat the space, convection. Unit heaters can create significant thermal stratification. That means the hot air will stay near the ceiling and cold air near the floor. IR heaters transfer the heat to the floor and the walls and then transfer that heat to the air. So all those floors, they participate in the transfer of the heat. Occupants can feel significantly cold with cold feet. With unit heaters, it will require much more input, heat input. You can say we put 200, maybe several 100,000 more BTUH with the unit heaters to achieve the same level of comfort we can achieve with IR heaters. Roberts-Gordon new reflector is even better. So you may not even need 200,000 BTUH to achieve what I have shown it to you. IR heaters provide you bigger bang for your buck. So with that, thank you so much for your attention.